the solids can be categorized into some types of bodies. So they are rigid bodies. What are rigid bodies? They have fixed shape, okay, and fixed size. That means you cannot change the distance between particles of rigid body. Then there is an elastic body, okay, perfectly elastic body, and a perfectly plastic body. So what's the difference between these two? Now, if you exert some external forces on rigid body, nothing will happen to the shape and size of rigid body. It will remain as it is. But for elastic body, if you apply some external force, suppose its length changes, okay, some of its property changes. Suppose its length changes. So then when you remove the external force, the length will come back to its initial form, okay, initial value, okay. So that is elastic body. And what is plastic body? When you exert an external force, there will be deformation. That means suppose length changes due to the external force. Now even if you remove the external force, that deformation will remain there, okay. So length will not be restored, right? So that is plastic body. Now ideally, okay, you all of these things, these are idealizations. So there is no body in the world, no solid in the world which is perfectly rigid or perfectly elastic or perfectly plastic, okay. So in practice, most of the bodies, they are partially rigid, you can say, and partially elastic bodies. So if you exert some external force, what happens? There will be some deformation in the body, and when you remove the external force, the body will not regain its original shape and size completely, but there will be some deformation left in practice, okay. So most of the bodies, or almost all the bodies in the world, they are partially elastic, not completely elastic, okay. So that is the practical case. All right, so now if I want to give some examples of perfectly elastic bodies or bodies which are close to perfectly elastic, so rubber, steel, they are almost perfectly elastic. That means when you exert force on rubber, okay, you have some rubber, suppose you stretch it, it will get elongated. You remove the external force, it will almost come back to its original form, okay. So likewise the steel is also almost perfectly elastic. Then perfectly plastic bodies, clay, wax, okay, these are perfectly plastic. If you take lump of clay, then you exert some force on it, you deform it, it will stay in that form only, okay, it will not regain its original form. So this is clear. These are just some bunch of definitions. All right, now what is elasticity? So elasticity, it is property of material due to which it regains its original shape and size, okay. So where does it come from? So let's suppose you have some material. We know everything is made up of atoms or molecules. So let's suppose we have this wire and we exert some external force on it. Suppose we apply some weight to it. What happens? It will get elongated. Its length will increase. Okay. So now when you remove that weight, it will come back to its original length. Okay. Why does this thing happen? It's because everything is made up of atoms or molecules. And if you consider these atoms, suppose, okay, so we have zoomed the wire and we are looking at the atoms. There will be bonds between the atoms. So these bonds are spring-like between atoms. If it is made up of molecules, then between molecules there will be bonds. So these bonds are spring-like. What does it mean? So atoms want to stay at a fixed distance called as equilibrium distance away from each other. If you push them close to each other, they don't like that. What does it mean by they don't like that? So they settle at a fixed distance. If you push them close to each other, there will be repulsive force. If you increase the distance between them, there will be an attractive force. Okay, if you pull them apart, there will be an attractive force. So the forces are spring-like. Okay, for a spring, if you decrease the distance, there will be elongation. Sorry, there will the spring will try to regain its shape, regain its original length. Okay, when you stretch it again, it will try to compress itself. Okay, due to the spring force. So these bonds between the atoms or molecule, they are spring-like. Okay, and because of these bonds, what happens that when you exert some force, then suppose you are applying a force in order to increase the length of this body, so these bonds will get stretched. Okay, when you remove the external force, what will happen? So again, these spring-like bonds or these springs, you can say, they will try to regain their original length. And that's why what happens when you remove the external forces, body regains its original shape and size. Okay, and this property of the body, it is known as elasticity. Okay, so is this thing clear? So now this elasticity of a body, it has got particular limit. You keep on increasing the external force, then what will happen? There will be some point. There will be some point of the external force when this elastic property of body will break down. Okay, so that is the maximum tension or maximum external force, deforming force this body can bear. Okay, after that body will be no longer elastic. So you can think of it like this: you have these bonds between the atoms. If you pull them apart, what will happen? At a particular distance, then at a particular distance, the attractive force will be not as much as required to retain their to regain their original distance. Okay, come back to the original equilibrium distance. Is this thing clear? Yes, no? Okay, so there will be a particular limit beyond which you cannot, beyond which if you increase the force, what will happen? The body will not regain its original shape and size. Okay, so body will lose its elastic property. All right, so now there are a lot of definitions. Okay, so one of the definitions is stress. So what is stress? It is internal restoring force per unit area of a body. So for an example, you have this wire and you apply this weight to the wire. Okay, so when you apply this weight on the wire, what happens? We have discussed earlier that there is a tension developed in the wire. Tension will be upwards. Okay, so now what is that tension? So tension is nothing but the internal restoring force. Okay, tension is the internal restoring force. So when you apply this weight is acting downwards, the internal restoring force will act upwards. And in equilibrium, the value of this internal restoring force will be equal to the external force applied. Okay, so stress is defined as this internal restoring force, which will be equal to the external force only, okay, divided by area, right? Divided by area. So now, depending upon various conditions, there are various forms of stresses. One is longitudinal stress. So what is longitudinal stress? If you apply an external force in order to change the length, then we have to consider longitudinal stress. Okay, so as in this case, we are trying to change the length of this body. Okay, so you can say for linear bodies, the stress that we need to consider is the longitudinal stress. Okay, if external force changes length of a body, then the stress applied is longitudinal stress. It is denoted by letter sigma. Okay, stress is denoted by sigma in general. So it is force upon area. What is force? Force is equal to mg. And what is A? A is the cross sectional area of the wire. Okay, so this is longitudinal stress. Then there will be volume stress. So again, meaning is clear from the name itself. So what is volume stress? The stress applied in order to change the volume. Okay. For an example, you have this body which is submerged in water, right? So there will be pressure acting on this body from all sides due to the water. Okay. What is pressure? Pressure is force per unit area. So there is, you can say, force acting on this body due to the water. And what will happen because of this force? The volume of this body will change. The volume of this body will decrease in particular. So this kind of stress which changes the volume is known as volume stress. Okay. Volume stress is equal to what? Again, force upon area. So here force is acting on all sides uniformly, and therefore force upon area can be called as what? Pressure. Okay, so volume stress is equal to pressure. It is also known as bulk stress. Okay, bulk meaning it changes the bulk. I'm sorry. So we call it either volume stress or we call it bulk stress. Okay, it changes properties of body in bulk, we can say. So this is another form of stress. Then there is another form which is known as tangential stress. So for an example, consider this book. Okay, you have some book, you keep your hand on that book and you push your hand like this. Okay, you put your hand on the top cover and you slide your hand. What will happen? So this top cover, it will slide like this, and there will be some distance through which this will move. Okay, so what is this force doing now? This force is along tangent, you can say it is tangential force, tangential to the top surface, and it is changing shape of the body. So this force or this stress, which is, so force is in which the force is tangential and it is changing stress of the body. This one is known as tangential stress, or there is another name, it is known as shear stress. So how will you define it? So suppose you have this cube, okay, you apply a force in this direction on the top surface and it is parallel to the top surface. That's why tangential. So the force is parallel to the top surface and area of the top surface is suppose A. So this tangential stress or shear stress, it is defined as what? F upon A. Okay, is this thing clear? These stresses? Yes, no? Is there any question? Okay, good. All right. So this is stress. Next, we'll define stress. So, sorry, we'll define strain. What is strain? The change in configuration, some property of body divided by original configuration. Okay, change in configuration divided by original configuration. So when we apply a longitudinal stress on a body, what happens? Some strain is, some longitudinal strain is developed. So what is that longitudinal stress? Sorry, strain. So it is change in length upon original length. So in this case, the configuration is length, change in length per unit original length. Then there is next kind of strain when you apply the volume stress or bulk stress. What happens? Volume changes. So here configuration is volume. So volume strain is equal to what? Delta V divided by V. Okay. And shear strain. So shear strain is shift in this top layer. Okay, shift in position of the top layer. How much is the shift? So this x is the shift divided by its distance from the fixed layer. So this bottom layer is fixed. Then we define shear strain as this x shift in position of top layer divided by its distance from the bottom layer. So x upon L. Okay. And in terms of this angle, which is known as shear angle also, it is equal to tan of theta. Okay. It is equal to what? Tan of theta. right? So longitudinal strain is delta L upon L, volume strain is delta V upon V, and shear strain is just X upon L, which is equal to tan of theta. Okay, this is clear. Okay. So then now we know the Hooke's law. What is Hooke's law for a spring? That extension produced in a string is directly proportional to the force, right? So restoring force is directly proportional to what? The displacement. Okay. So now if we divide restoring force by area, considering area will remain constant, and this x by L. Okay, what is L? L is the original length. Suppose x is change in length, L is original length. So what do we get? We get stress is directly proportional to strain. So Hooke's law says under the elastic limit, under the elastic limit. So till the time body is elastic, stress is directly proportional to the strain. Okay, stress is directly proportional to the strain. And the proportionality constant between stress and strain, it is known as modulus of elasticity. So if you remove the proportionality sign, an equality sign will come. So this proportionality constant is known as what? Okay, and a constant will come. That constant is known as what? Modulus of elasticity. So depending upon three types of stresses and strains, there are three moduli of elasticity. Okay, so first one is known as Young's modulus. So Young's modulus is longitudinal stress divided by longitudinal strain. Okay, longitudinal stress divided by longitudinal strain. So suppose you have some wire, you have a wire like this, and you apply some weight on it. You apply some weight on it. So weight is equal to mg. Okay, area of cross section is A, suppose. So longitudinal stress is equal to mg upon A. And what is longitudinal strain? Delta L, which is change in length divided by original length. Okay, so dividing by delta L upon L is multiplied by its reciprocal. Okay, so reciprocal is what? L upon delta L. And that's why you have Young's modulus equals to what? mgl divided by A into delta L. Okay, this is Young's modulus. This is clear? Okay, so maybe in this chapter there won't be any doubt. This is very, very straightforward. Okay, next one, bulk modulus. So what is bulk modulus? Bulk modulus is volume stress divided by volume strain. Okay, volume stress upon volume strain. What is volume stress? Volume stress is pressure, right? So it is pressure divided by volume strain is delta V upon V, change in volume per unit original volume, right? But there is this negative sign. So can you guess what is this negative sign doing? Simple. When you increase the pressure, what will happen to the volume? Volume will decrease, right? So that's why you have negative sign. Now you can write it like this is in denominator delta V by V. So you can write it like what? Minus P multiplied by V upon delta V. Okay. So this is bulk modulus denoted by B. Next one is shear modulus. Okay. What is shear modulus? It is also known as modulus of rigidity, because if shear modulus is greater, that means you need to apply greater stress in order to change the shape of the body. Okay, and the body whose shape cannot be changed is rigid body. So how rigid is the body? Measure of that thing is modulus of rigidity. Okay, so shear modulus is denoted by letter G, and it is shear stress divided by shear strain. What is shear stress? Again, it's tangential force divided by area. And what is shear strain? It is X upon L. the lateral displacement of a layer, okay, shear strain is x upon L, where x is lateral displacement of a layer and L is the distance between that layer which is getting displaced and fixed layer. Okay, so shear shear modulus G can be written as what? F into L divided by AX, or F upon A into tan theta, because x upon L is equal to what? Tan of theta. Okay, so this thing is clear till this point. Okay, and there is one more definition. There is one more definition which is the reciprocal of bulk modulus. It is known as compressibility. Okay, so I will just write it here. Should be in notes. Don't know. All right. So compressibility is just equal to 1 upon B. Okay, 1 upon bulk modulus. Okay. So if bulk modulus is large, means you need to apply a large pressure in order to compress a body. Okay. So measure of compressibility of body is what? Reciprocal of bulk modulus, right? So bulk modulus is small, means body is more compressible. Okay. Compressibility is denoted by letter K or kappa. In some texts, it is denoted by C only. Okay. And it is just reciprocal of bulk modulus. Okay. Then we'll come at the stress versus strain curve. So what is stress versus strain curve? So what you do is, in order to study the elastic property of body, you take a body, for an example, you take this wire and you apply some force, apply some stress on the wire. So this stress is increased gradually and you study the strain in the wire. Okay, and you plot the graph of stress that you apply versus strain developed in the wire. Okay, so what you do is you keep on measuring the change in length whenever you apply some weight. Okay, weight means, so when you apply some weight, some stress will be produced. Okay, so see, this is the graph of stress versus strain and it looks like this. Okay, so from here to here you can see that stress and strain, they are proportional to each other and therefore the graph is a straight line. Okay, so till this point, if you increase the stress, the strain will increase accordingly. Okay, if you increase, let's suppose the stress by 1 unit, strain will increase by 1 unit. If you increase it by 2 units, then the strain will increase by 2 units, for an example. Okay, so the graph between them is a straight line. They are directly proportional to each other. So it is straight line till this point A. So this point A, the stress corresponding to this point is known as the proportionality limit. Okay, it is known as proportionality limit, right? So after that, again, you keep on increasing the stress and you note down the strain. So what happens is, now the wire, so compared to this previous case from O to A, if you see A to B, what happens? More strain is developed for lesser stress. Okay, more strain is developed for lesser stress, and the graph between stress and strain, it is curved. So it's no longer a straight line. Okay, but wire is still elastic. Okay, so this point B corresponds to the elastic limit, or it is also known as yield point. So what does it mean? So if you just remove the external stress, what happens? The wire will regain its original shape and size. It will regain its original length till the point B. And that's why this point B is known as what? Elastic limit. So they keep on measuring this thing. They increase the stress. Then they remove the weights and check whether the wire is coming back to its original length. So it comes back to the original length till the point B. That means wire is still elastic. It doesn't obey the Hooke's law, okay, because stress and strain, they are not directly proportional. So this graph is curved from A to B, but still wire is completely elastic. And after this point, it is no longer completely elastic, okay, and that's why the stress corresponding to this point, it is known as elastic limit, and this point is also known as yield point. Okay, why is it known as yield point? Because now at this point you can see graph between stress and strain, it's almost flat. Okay, that means you're not applying any stress, you're not changing the stress, but there is still some strain. There is still some strain. Okay, so wire is yielding for very less increment in stress. What's happening? A lot of strain is produced, a lot of change in length is produced. Okay, so wire is yielding here. Yielding meaning it's it's not that elastic. Okay, yielding meaning its length is increasing of its own. Okay, or you can say for very short increment in stress, its length is increasing a lot. Okay, so this is also known as yield point. So this thing will keep on happening till point C. Okay, so till the point C. Now what happens? So after point B, the wire is not completely elastic, but still it will regain some of its original length. Okay, so now if you remove the weights at point C, you can see what happens. So this much amount of strain, it remains in the wire. Okay, you are removing all the weights, still this much amount of strain remains in the wire, and this is known as permanent strain, or it is also known as permanent set. Okay, so what is permanent set or set? It is when you remove all the forces, deforming forces, still some amount of strain is left in the material. It is known as permanent strain or set or permanent set. Okay, is this thing clear? Yes, no? So this graph is important. There can be question just based upon this graph. Okay, because there are not many things in this chapter. Okay, after this point, again what happens is you have to apply more stress for same amount of strain, you can say. Okay, so the graph goes like this. Okay, and you get another point, point D. So at this point what happens? So here this is the maximum stress that the wire can bear at the point of maximum tensile strength or maximum tensile stress. Okay, this is tongue twisting. So at the point of maximum tensile stress, what happens? Even if you reduce the stress after that point, still what happens? The strain increases only. Okay, strain increases only, and then now you go on decreasing the stress gradually, still the strain keeps on increasing, and at this point E, what happens? A neck is formed in the wire. Okay, so neck like this. So this is suppose your wire, neck is formed, and the wire breaks. Okay, the wire breaks at this point. So this is known as fracture point. So the neck will be formed between this and this point somewhere, and the wire will break at this point. This is known as fracture point. Okay, so is the graph clear, or is there any doubt? Okay. Now, based upon this graph, to see if this region between D and E is very close, then the material is brittle. So the point at which you can say neck is formed, okay, this is the point at which neck is formed, and point at which wire breaks. If these 2 points are very close to each other, then neck is formed, wire breaks. So this kind of material is brittle. Okay, and if D and E are separated by a large distance, if they are separated by a large distance, okay, that means the material is ductile. So what does it mean? That means you can shape that material in form of very thin wires. Okay, so that kind of material is known as ductile material. So if distance between D and E is very short, then the material is brittle. If the distance is very large, then the material is ductile. Okay, this is clear? Yes, no? Okay. These are very simple points. I don't know how to explain simple points even simply. Okay. Anyways, after that, there is another definition, and it is Poisson's ratio. What is Poisson's ratio? Poisson's ratio is lateral strain divided by longitudinal strain. Okay. So for an example, when you pull on a wire, its length will increase. What will happen to its diameter? Its diameter will decrease. Okay, its diameter will decrease. So lateral strain is change in diameter per unit original diameter, and longitudinal strain is change in length upon original length. So Poisson's ratio is what? It is the ratio of lateral strain to the longitudinal strain. And why is this negative sign? Because if you increase the length, diameter will decrease, right? So that's why you have this negative sign. Okay. So what is elastic potential energy? When you exert some force, what happens? The length of this body changes, length of this wire changes. Okay. So you are exerting some external force, means you are giving some external energy, okay, in doing this work in order to change the length. So this external energy that you give, it is stored as the elastic potential energy of the body. Okay. So how much is that? It's equal to the amount of work done, right? So we know that dw equals to f dot dl. Okay, and now we know the relation between this force and the Young's modulus. So y is equal to what? Y is equal to stress upon strain, that is f upon a, multiplied by change in length is suppose small l. Okay, original length is capital L. So multiplied by L upon small l. So therefore f can be written in terms of these other things. F is equal to ya into small l upon capital L. Okay. So for small change in length, dl, what you can say, f is equal to ya into dl upon capital L. So okay, so suppose change in length is suppose L. Okay, I'm sorry. Change in length is suppose L. So you get f is equal to yal upon small l. So length is changed to L, and now suppose you are again changing it by dl. So force is yal upon small l, and you are increasing the length further by dl. So work done will be equal to yal upon capital L multiplied by dl. And then you integrate this. Okay. So total change in length, suppose delta L, then you get this formula. So work done will be equal to what? Half of the external force multiplied by delta L. Okay, after integrating you get this. Work done is equal to half of F multiplied by delta L. So this is work done or elastic potential energy. It is equal to half of load. Load is external force multiplied by the extension. Half of load into extension. Okay, this formula we need to remember. Work done or the elastic potential energy of the body is half of load into extension. Okay, this is denoted by small u. So small u is equal to what? Capital U divided by V. It's elastic potential energy per unit volume. So you have this formula for the elastic potential energy. If you divide it by volume, what do you get? So this formula is half of F into delta L. Okay, volume is, you can say, area multiplied by length. Okay, so you have force upon area, right? If you write volume in the denominator, which is A into L, you have F upon A multiplied by delta L upon L. So this is equal to stress and this is equal to strain. Therefore, you get small u is equal to half of stress into strain. Okay, it is half of stress multiplied by strain. Then you use y equals to stress upon strain and you get another relation. So here you write stress is equal to y into strain. So you get another formula for the elastic potential energy per unit volume. It is half of y into strain square. Then again, in place of strain, what you can say, what you can write. So if you take strain on this side, y on this side, you get strain equals to stress upon y. You get this another formula that u, the elastic potential energy per unit volume, is half of stress square upon y. Okay, so this is clear. Okay, all right. So then in this one, there is one more thing that we should remember, and that thing is here. Okay, force is equal to ya upon L multiplied by extension. Okay, force is equal to ya upon L multiplied by extension. Ya divided by original length multiplied by extension. Okay, we can find it out, but if we remember it, it will be faster. Then now sometimes, not sometimes, suppose there is some increment in temperature. Okay, what happens due to increment in temperature? The length of wire can increase. Okay, so that means some strain is produced. Okay, length of wire increases means some strain is produced. So if strain is produced, there must be some stress. So that stress, okay, strain produced due to what? Increment in temperature is known as thermal strain, and the stress developed is known as the thermal stress. Okay, so suppose delta T is rise in temperature, due to which length of wire changes by delta L. So this is change in length. So this delta L will be directly proportional to delta T. More is the increment in temperature, more will be change in length, more will be increment in length. Okay, or if temperature decreases, there will be some decrement in length. So the change in length is directly proportional to change in temperature. Then the change in length is also directly proportional to the original length, right? It's directly proportional to the original length. Suppose length of wire is 5 centimeters, it changes by 1 mm due to 1 degree change in temperature. Length of wire is 10 centimeters, it will change by 2 mm. Okay, so it's directly proportional to length also, and that's why you can write delta L is proportional to L and delta T. You multiply these two, so you get delta L is equal to this constant alpha multiplied by L delta T, and this constant alpha, it is known as coefficient of thermal expansion. Okay, or this is actually known as linear coefficient of thermal expansion. right? So then, now this is change in length. What will be strain? Strain is equal to change in length upon the original length. Take this L on other side. So you get delta L upon L is equal to alpha delta T. Okay. Thermal strain is alpha delta T, right? And what will be thermal stress therefore? So we know that stress is equal to Young's modulus multiplied by strain, and therefore thermal stress is equal to Y multiplied by thermal strain. Thermal strain is alpha delta T. Okay, so this thing is clear. So thermal stress will be Y into alpha delta T. Yes, no? Okay. All right. So now this much is theory of this chapter. There haven't been lot of questions, but you can expect one question from this chapter. Okay, so let's see some questions. Shearing stress is related to, tell me, shape of the plate, shape of the body. Okay, longitudinal stress is related to length. Volume stress is related to volume. Okay, a bulk stress is related to volume, and shear stress is related to shape. Next one, if angle of shear is 30 degree for a cubical body and the chain length is 50 centimeter, then the original length of cube is. Okay, tell me. Tan theta equals to x by L. X is given, right? Theta is given. L is equal to x by tan theta, right? This is very, very simple. How much is x? 250 centimeter. Options are in meter. So let's convert this to meter. So it is 2.5, right? And how much is tan of 30? Tan that 1 by root 3, right? Right. So it is 2.5 multiplied by, so divided by 1 by root 3 is multiplied by its reciprocal. So multiplied by root 3. And root 3 is how much? 1.1.732. Okay. So which of these would be the answer? Tell me. Can you guess? Looking at the answers, can you guess? This is simple, right? See, it is if you take 2.5 times 2, you will get 5, right? So this is not 2, this is less than 2. Okay. So it can't be 5.3, it cannot be 5.5. And yeah, it's option D. And this is also very close to 5. Okay, so not these three, this one. Option D is the answer. Good. Let's see next one. This is recent one. Okay, 2020. A wire of length L, area of cross section A, is hanging from fixed support. The length of wire changes to L1 when M is suspended from its free end. The expression for Young's modulus is. Tell me. It's option D, right? Okay, it is change in length will be equal to what? Final length upon original length. Okay, and therefore Young's modulus is what? Mg upon A divided by change in length upon original length, which will go to the numerator, which is mg upon A multiplied by L upon L1 minus L. Yeah, it's option D. Good. Next question. Two wires are made of same material and have same volume. The first wire has cross-sectional area A and second wire has cross-sectional area 3a. If length of first wire is increased by delta L on applying F, how much force is needed to stretch the second wire by the same amount? Tell me, what can we do? Okay. So y is equal to what? F upon A multiplied by delta L, okay, upon L. So in numerator, you can write the capital L. So as I said, if you remember either the formula for F or formula for delta L, actually we can find it out. So what will be delta L from this? FL upon AY. Okay. So just remember this formula, delta L is equal to FL upon AY, right? So what's given that extension is same. How much force is needed to stretch the second wire by same amount? So extension is same. That means delta L1 is equal to delta L2. Okay. So let's write F1 L1 upon A1 Y1 is equal to F2 A2 upon, sorry, F2 L2 upon A2 Y2. Okay. So the wires are made up of same material. That means Y1 is equal to Y2. Okay. And have same volume. So now we have to relate the area and length. Okay. So first wire has cross-sectional area A and second wire has cross-sectional area 3A. Okay, that's fine. Second wire has cross-sectional area 3 times of first one. So if I cancel this out, what will remain there? 3 will remain. Okay. And you want now the ratio of F1 is to F2. So I can say it's F1 is to F2 equals to L1 upon 3L2. So do you know L1 upon L2? Yes, no, not given. It is not given, no. But there is something which will tell us about L1 upon L2. What is that thing? That V1 is equal to V2. Okay. So what is V1? What is volume of a wire? It is area into length. Very good. Area of first wire multiplied by length of first wire is equal to area of second wire multiplied by length of second wire. So that is, you want L1 upon L2, L1 upon L2, it will be equal to what? A2 by A1. So that's equal to 3. Okay. So put that here. Okay. So therefore you get 3. Oh no, 3 upon 3. Am I correct? A2 is equal to 3 times A1. That is fine. And here you have F1 by F2. Oh, it is L2 upon L1. Okay. So therefore, what do you get? L2 upon L1 will be 1 by 3. Right. It will be 1 by 3. And therefore it will be 1 by 9. Okay. So what do you get then? F2 is equal to 9 times F1. Okay. F2 is equal to 9 times F1. Right. So this is clear. Okay. Actually, I have solved this question many times, so I kind of remember the answer. And that's why I was surprised that it's coming out to be same. Okay. Anyways, so I had done a mistake here. All right. So F2 equals to 9 times F1. Next question. The bulk modulus of spherical object is B, if it is subjected to uniform pressure P, the fractional decrease in radius is, tell me. B is equal to minus P into V upon delta V, right? So you want fractional decrease in radius. So V is equal to 4 by 3 pi r cube, and therefore you have from first chapter delta V upon V will be equal to 3 times delta R upon R, right? So from here you can find out delta V upon V. So delta V upon V is equal to what? Minus P upon B, right? If I take this on this side, minus P upon B. And this is 3 times of delta R upon R. So we can put that here. It is 3 times of delta R upon R is minus P by B. And therefore delta R upon R will be how much? Take that 3 on upon 3B, right? Exactly. It will be minus P upon 3B. Good. So it's option. There is no negative sign. So they want only magnitude. Option C. Okay. Let's see next question. The Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from same roof. Okay. If we want the lower ends of wires to be at the same level, that means original length is same, delta L must be equal, right? Delta L must be equal. If we want if we want the lower ends of wires to be at same level, then the weights added to the steel and brass wires must be in the ratio of. What must be the weights? So we want to find out F1 is to F2, or if we call it steel and brass, if we put suffix S and B, Fs is to FB. Okay. So we remember this formula delta L. We just discussed, we have to remember this. Okay. It is FL into AY. Okay. So delta S, delta L for steel is equal to delta L for brass. Okay. So F for steel, L for steel, A for steel, Y for steel. Okay. In exam, don't do this. Okay. You can just say F1, L1, A1, Y1. Okay. Just put suffix 1111 and 2222. So this will be, and what is given then? We want to find out Fs is to Fb. Lengths are equal. So this gets cancelled. What else is equal? Same area of cross section. So this thing also gets cancelled. Okay. So we have Fs is to Fb equals to Ys is to Yb, right? 2 is to 1. Okay. So this is very, very simple question. And all questions on this chapter are simple. Okay. Let's see next one. The approximate depth of ocean is 2700 meters. The compressibility of water is 45.4 multiplied by 10 raised to minus 11, okay, per Pascal, right? And density of water is 10 raised to 3 kg per meter cube. Okay. What fractional compression of water will be obtained at the bottom of the ocean? Tell me. Right. Compressibility is inversely proportional to bulk modulus. So just write bulk modulus in denominator, PV upon delta V. That delta V will go to the numerator, right? I have just written 1 upon bulk modulus. Okay, and bulk modulus is PV upon delta V. So what fractional compression of water will be obtained? Okay, so you want, just take that P on this side, nothing else. You want delta V upon V, okay, or minus delta V, that is compression, minus delta V is the compression, right? So fractional compression is minus delta V upon V. It will be equal to this K times P. K is how much? 45.4 multiplied by 10 raised to minus 11, and pressure. So pressure is not given. You are given with the depth of ocean, density of water. Okay, so you know what is pressure. It will be equal to rho g. No, pressure. So suppose you have this ocean, suppose, and its density is rho. So pressure at depth d, P will be equal to rho g h. Okay. So it comes in the next chapter, but this formula is regular formula. Pressure is equal to rho g h, right? So rho g h is 45.4 multiplied by 10 raised to minus 11. Rho is how much? 10 raised to 3. Okay. This thing we need to remember because sometimes they don't give it. Density of water is actually a standard value, 10 raised to 3 kg per meter cube, 1000 kg per meter cube. And with respect to this density, we measure densities of other bodies. Okay. So this thing we need to remember. Density of water is 10 raised to 3, 1000 kg per meter cube. All right. So G is 10, H is 2700. So there is a lengthy calculation, or there is some calculation. Let's see. So we have what, 10 raised to 3. This is 10 raised to 4, 6, and this will be minus 11 plus 6 is 10 raised to how much? Minus 5. Minus 5. Okay, so we have 45.4 multiplied by 27 multiplied by 10 raised to minus 5, and we have to multiply this 45, or let's just multiply 45 with 27, right? 7 5s are 35, carry 3, 7 4s are 28, 28 plus 3 is 31. Okay, so then 2 5s are 10, 10 carry 1. Okay, put 0, carry 1. 4 2s are 8, 8 plus 1 9. So 5 1 9 plus 3 is 12. Okay, 1 2 1 5 multiplied by 10 raised to 5, or you can say 1.215 multiplied by 10 raised to 3 into 10 raised to minus 5. Okay, so that is 10 raised to minus 2. So answer is option A after a little bit of calculation, right? Okay, but problem is not difficult. It might take little bit more time. Okay, but this is sure shot within 1 minute or so, 1 minute, 1.5 minutes. This is sure shot. Okay, 4 marks. All right. Next question. Copper of fixed volume V is drawn into wire of length L. When this wire is subjected to constant force F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? Tell me. Okay, it's not that straightforward. I'm sorry. Copper of fixed volume V is drawn into a wire of length L. Okay. When this wire is subjected to a constant force F, the extension produced in delta is delta L. So you can tell me what is delta L? FL upon AY. Okay. And what else is given? Copper of fixed volume V. This is important. Okay, volume is fixed. That means V is constant, right? So V is constant means area times length is constant. So right now we want delta L is proportional to what? Okay. So F and Y, they are constants because uh, it is subjected to a constant force. So Y is constant, F is constant, A is not constant. Okay, A is not constant, L is not constant because you are changing the length. So area of cross section will also change. So what we have to do is we have to adjust a constant here. What we can do, either we can multiply with A in numerator so that we get volume in the numerator. So okay, either we have to multiply and divide by A so that we get volume in the numerator that is constant, so it will be inversely proportional to A square. But we are asked about L, okay, the power of length to which it will be proportional to. So that's why what we'll do, we'll multiply and divide by L. Okay, so it is F upon Y, which is a constant, multiplied by L upon A. Okay, this is the thing. And then I will multiply and divide by length. Why? Because area into length, volume is constant. Okay, so these things are constant now. Okay, this is also constant, and therefore I can say it is delta L is equal to some constant into L square. So delta L is proportional to L square. Okay, this is clear. So if delta L is proportional to L square, which one will be a straight line? Delta L versus L square, right? Is it clear? Good. Next one, the following four wires are made of same material. Which of these will have the largest extension when the same tension is applied? Okay, tell me. We have to find here. This is lengthy question. Okay, which one will have largest extension? So we have delta L equals to what? FL upon AY. Okay, area is equal to pi r square. Good. So F is same, Y is same, and area is pi r square. Okay. So diameter is given. Right. So it will be FL upon area is, you can say, pi diameter square upon 4. That upon 4 will go to the numerator, and that Y is there. So everything else is constant. Right. 4 F, pi is constant, Y is constant. Okay. So delta L is proportional to what? It is L by D square. So you have to find this quantity for all of these things because L and D is given. So in whichever option it is maximum, the length will be, change in length will be maximum, extension will be maximum. Okay. So let's do that. So this is 200 centimeter. Let's check in A. Okay, it is 200 in A. It is 200 divided by D square. So D square is 4. This is 50. In B, it is 300 divided by D square is 9. How much would this be? Okay, close to, yeah. So this will be so 33.33, because if I divide by 3, it will be 100, and okay, I can say it is 100 by 3. So 33.33. Next one is 50 and 0.5. So 50 divided by 0.5 square is 0.25, and yeah, so I will just multiply this by 4 and divide by 4. Okay, why? I am making the denominator 1. 0.25 into 4 is 1, right? So it's 50 times 4, that's 200. And D is 100 divided by 1. So this is just 100. 1 square is 1 only. Okay, 100. So it is option C, right? If my calculation is correct. Okay, this is simple question. There is nothing else, but little bit lengthy calculation, nothing else. Okay, because we have to solve it for 4 things, 4 options, verify for 4 options. That's why. Okay, good. So I don't expect there would be any doubt in any of the questions in this chapter. Okay, let's see next one. If the ratio of diameters, length and Young's modulus of steel and copper wires shown in the figure are P, Q, S respectively. Okay, so this is ratio of diameters, diameter of steel wire. There is one steel wire and one copper wire, diameter of copper wire. So 3 ratios are given, P, Q, S. First one is for diameter, second one is length, and third one is Young's modulus. So this is P. Then length of steel upon length of copper is equal to what? It is equal to Q, and Young's modulus of steel upon Young's modulus of copper is equal to S, right? Then corresponding ratio of increase in their lengths would be. Let's solve it. So we know formula for delta L. It is okay, FL upon AY. Okay. So this is again for steel, it's not equal. We want to find the ratio. I'm sorry. So delta L is equal to FL upon AY. So delta L for steel upon delta I'm sorry, L for copper will be equal to FL upon AY for steel, FL upon AY for copper. Okay. That is what is S. So in wire, no. See here for copper there is 5m weight. For steel there is this 2m weight. Very good. 2m plus 5m. Okay, because this weight is also supported by the steel. Okay, then tension in this wire will be 2m plus 5m, 7m. Good. So this is 7m multiplied by length of steel. Okay, we'll write it like this: length of steel upon area of steel into Y for steel, and multiplied by this thing F for copper. No, in it will be in denominator. No, F for copper is 2m, not 2m, 5m, multiplied by length of copper is how much? LC, and divided by AC into YC. Okay. So it will be 7 by 5, mm gets cancelled, multiplied by length of steel upon length of copper, multiplied by, you have area of steel. Okay, this is area of steel, area of copper. So this will be proportional to diameter square. Okay, so this is diameter of steel square, and I will take that this thing on in denominator actually. So diameter of steel upon diameter of copper, you have square of that, multiplied by Young's modulus of steel upon Young's modulus of copper. And now we just have to substitute these ratios. So this is Q, this is P, So it will be Q upon P square S. Okay, right. So what is the answer? 7 by 5 Q upon SP. No, right. It is SP square. Option B. Good. So there is nothing in this question also. Okay. Let us see next one. Two wire of same material having radius in ratio 2:1 and lengths in the ratio 1:2. Same force is applied on them, then ratio of their change in length will be. Again, you have to find delta L1 upon delta L2. So it is F1 delta L is what? FL upon AY. F1 L1 upon A1 Y1 and divided by F2 L2 upon AY2. So that 2Y2 will go to the numerator. Okay. So same material and same force means good. So this thing gets cancelled. Ratio of length is given. It's 1:2, 2:1. No, ratio of radius is 2:1. Ratio of length is 1:2. So L1 by L2 and this will be R2 upon R1 square. Area is proportional to radius square. So it is R2 upon R1 square. Right. So this thing is R1 is to I2, R2 is 2:1. So R2 is to R1 will be 1:2. Okay. So you have 1 by 2 for L1 by L2 and this is 1 by 2 square. So that is 1 by 4 into 1 by 2, 1 by 8 is the answer. Okay, good. This one, the Young's modulus of material of wire of length L and radius R is Y. If length is reduced to L by 2 and radius R by 2, the Young's modulus will be. Tell me. Mhm. L. See, here Young's modulus of material of wire is given. It is Y. Okay. And Young's modulus of the material is asked. So does it change? Young's modulus for a material will be fixed? No. So why are you saying FL upon AY? Okay, so it is Y only, right? So this is like they are playing with your mind. Okay, they are giving some values. This thing is changing, that thing is changing. Okay, what happens to Y? Right? Okay, so this is very simple. Young's modulus remains as it is. Next question. When a block of mass M is suspended by a long wire of length L, the length of wire becomes L plus small l. Okay, this is extension. The elastic potential energy stored in extended wire is, tell me. Very good. Elastic potential energy U is equal to half of load into extension. Good. Okay. So load will be mg, extension is small l. It is option D. Very good. Next one, wires A and B are made from the same material. A has twice the diameter and 3 times the length of B. The elastic limits are not reached when each is stretched by same tension. The ratio of elastic energy stored in A to that in B is, tell me. Same material, that means Young's modulus is same, okay, and A has twice diameter and 3 times length of B. Okay, if elastic limits are not reached, then when each stretched by same tension, so same force is applied. Okay, tell me the ratio of elastic energy stored in A to that of B is. Okay, so elastic energy, we want ratio of elastic energies. We can start like this, right? This thing is required. So it is half of load into extension, half of F into L, half of F into is delta L, let's say. Okay, this will be half of F1 delta L1, F2 delta L2. We can start like this, right? Then what is given? Each is stretched by same tension, so force is same. That means it is just delta L1 by delta L2. Okay. So again, what is delta L? FL upon AY. Okay. FL F1 L1 upon A1 Y1 multiplied by this will be A2 Y2 upon F2 L2. So again, same force, same Young's modulus, same force, same Young's modulus, right? So then you have U1 is to U2 equals to L1 is to L2, and what else is given? Diameter is given. Diameter A has twice the diameter and 3 times length of B. So this is proportional to diameter square. So diameter of 2 upon diameter of 1 square. Okay. 1 is A and 2 is B. So A has twice the diameter. So D1 is equal to 2 times D2. Okay. So here we should not make mistake. D1 is 2 times D2. Okay. And L1 is 3 times L2. 3 times. So this is 3 times L2 upon L2. So this thing will get cancelled. This thing will get cancelled. 1 by 2 square is 1 by 4. Right. So answer would be 3 by 4. It is option B. Okay. This is simple, right? Okay. Good. So see, if you can't arrive at the answer directly, you can start with the condition given in the problem. So this thing is given. Then some way will come. Okay. Some way will come out. So here, as you can see, F1, F2, this thing gets cancelled. Then you get this thing. So now you can find out this thing. You know what is delta L? Delta L is what? It is FL upon AY. Okay. All right. Let's see next one. Young's modulus of material of wire is Y. On pulling the wire by a force F, the increase in its length is X. The potential energy of the stretched wire is which one? Option A. Okay. Next one. Two wires of same material and same diameter have lengths in ratio 2 is to 5. They are stretched by same force. The ratio of work done in stretching them is. So again, this is similar question to that of what we have seen. So ratio of work done W1 is to W2 is half of load into extension, half of F1 into delta L1, half of F2 into delta L2. So same diameter and they are stretched by same force. So this thing gets cancelled. So it is delta L1 upon delta L2. Okay. Can you find out delta L1 by delta L2? Exactly. It will be 2 is to 5. Why? Because their lengths are in the ratio of 2 is to 5. So the extension will be directly proportional to original length because Young's modulus is same, diameter is same. Okay, delta L will be proportional to original length. Okay. and therefore you can say it is just L1 upon L2. Okay, more is the length, more will be the extension. So this is 2:5. Very good. So it's option B. Okay. Next one, there is no change in the volume of wire due to its length on due to change in its length on stretching. Poisson's ratio of the I'm sorry material of wire is, tell me. Okay, so Poisson's ratio is minus delta D upon delta L. Okay, so now what else can you do? Volume is not changing. There is no change in volume of the wire. Okay. No, no, not diameter is not changing. See, volume is not changing. That means volume is constant. What is volume? Volume is area into length. Okay. So area is what? Pi r square. Okay. So can you find out delta V by V? How much will be delta V? Okay, it will be 2 times of delta R upon R plus 2 times of, plus delta L upon L. Why am I finding this? Because I have delta L upon L and I have delta D by D, which is equal to what? Delta R upon R only, right? Diameter. Okay. The ratio of change in diameter to original diameter will be just equal to ratio of change in radius to original radius. Okay. All right. So then that's why we are finding this. So this thing is zero because volume is constant, right? So this thing is zero. So this is zero. That means, okay, which implies delta V upon V is zero. Therefore, you get delta L upon L is equal to minus 2 times of delta R upon R. Or you can say minus 2 times of delta D by D, right? And you can put that, so minus delta D by D you already have, and in denominator you will have minus 2 times of delta D upon D. So this thing gets cancelled. Minus minus sign gets cancelled and it is 1 by 2. So that means it is 0.5. Option A. Okay, tell me. Right. So see, suppose radius is, okay, suppose radius is 5 centimeter and change in radius is 1 mm. Okay. Or let's take an example in centimeters only. Suppose radius is 100 centimeter, change in radius is 1 centimeter. Okay. So how much is delta R upon R? 1 upon 100. 1 upon 100. Right. So now if radius changes by 1 centimeter, diameter will change by how much? By how much amount will the diameter change? 2 centimeters. 2 centimeters, right? Okay. So now what is change in diameter upon diameter? 2 centimeter divided by diameter is 200. Okay. Okay. Or shall I? So 2 upon 200. That means it is 1 upon 100 only. Fractional change is same. Okay. Good. Let's see next question. A metal rod is fixed rigidly at two ends so as to prevent the thermal expansion. if L, alpha and Y respectively denote the length of the rod, coefficient of linear thermal expansion and Young's modulus of its material, then for an increase in temperature of rod by delta T, the longitudinal stress developed in the rod is, tell me, inversely proportional to alpha, inversely proportional to Y, directly proportional to delta T upon Y, independent of L. Tell me. Thermal stress, we know this, thermal stress is equal to Y multiplied by thermal strain. And what is thermal strain? It is alpha delta T, right? Alpha delta T. Or you can say thermal stress directly, you can remember by alpha delta T. Okay. So is it inversely proportional to alpha? It's not. It's directly proportional. Inversely proportional to Y? No. Directly proportional to delta T upon Y? No. Directly proportional to delta T, but not upon Y. Independent of L? Yes, independent of L. Okay, option D. Okay. Next one, two rods of different materials with coefficients of thermal expansion alpha 1, alpha 2 and Young's moduli y1 and y2 respectively are fixed between two rigid walls. Okay, between two rigid walls. They are heated to have same increase in temperature if the rods do not bend and alpha 1 is to alpha 2 is to 3, then thermal stresses developed in two rods will be equal when y1 is to y2 is equal to. Okay, so thermal stress is equal. That means y alpha delta t for first one is equal to y2 alpha 2 delta t2, right? And they are heated to have same increase in temperature. This thing also gets cancelled out. And you want, okay, thermal stress is equal. That's why I have equated thermal stress in first one to thermal stress in second one. Okay. So you want y1 is to y2. It will be equal to alpha 2 is to alpha 1. So it is 3 is to 2. Option C. Okay. This is simple. All right. So then this chapter ends here. Okay. So there haven't been many questions asked, but one question is asked frequently. And that one question, if you just study today's theory, okay, whatever we discussed, and the graph, stress versus strain graph, you study these problems and solve homework problems, I'm sure you can solve that one question. Okay, there is nothing in this chapter.